This video presentation will review some important concepts about thermodynamics from your first semester general chemistry course. Topics include definitions of energy, heat, and work, the definition of system and surroundings and state functions, and calculations involving standard enthalpies of formation and enthalpies of reaction. Let's start by reviewing the units used for energy. Energy is usually given in units of either joules, calories, or liter atmospheres. Here are some conversions between the different energy units. 1 calorie is defined as the energy required to raise the temperature of 1 gram of water by 1 degree Celsius. 1 joule is equal to 1 kilogram times meter squared per second squared. A calorie is also equal to 4.184 joules. And a liter atmosphere is 101.3 joules. For our purposes in this chapter, we will focus on one definition or type of energy that is the capacity to do work or to cause heat flow, as this is the most relevant for chemical reactions. To review, however, recall that energy is often subdivided into two main categories, kinetic energy and potential energy. Kinetic energy is the energy due to the motion of an object. The kinetic energy of particles is given by 1/2 mv squared, where v is the velocity of the particles. Potential energy, on the other hand, is the energy available due to an object's position. Within the category of kinetic energy, we can further classify energy as being mechanical, thermal, electrical, or radiant. Mechanical energy is the kinetic energy or motion of macroscopic objects. Thermal energy is the kinetic energy of atoms, molecules, or ions. Electrical energy is the kinetic energy of electrons in a conducting material. Radiant energy is the propagation of electromagnetic radiation through space. This is the energy of light and other forms of electromagnetic waves. Potential energy can also be classified as being due to gravitation, electrostatics, or chemical bonds. Gravitational potential energy is the potential energy of objects due to the force of gravity. Electrostatic is the potential energy of charged particles due to Coulomb's force, the attraction between opposite charges or the repulsion of like charges. Chemical energy is the potential energy stored in chemical bonds due to Coulomb forces between electrons and the nuclei in molecules. In your first semester general chemistry course, you learned the first law of thermodynamics, that the energy of the universe is constant. Energy cannot be created or destroyed, only converted from one form to another. The first law of thermodynamics, you do not talk about thermodynamics. Heat and work are the processes by which a system exchanges energy with another system or its surroundings. Heat is defined as the transfer of thermal energy between two bodies or systems that are at different temperatures. Heat is given the symbol Q, and Q can be calculated from ms delta T, where S is the specific heat of the substance in joules per gram degree Celsius, and this equation is valid for a system where heat energy serves to change the temperature of the sample. When Q has a negative value, we define that process or reaction as being exothermic. When Q is positive, we say it is endothermic. Work is the transfer of energy to an object by force acting over a distance. Work is given the symbol W. Work is equal to the negative of the external pressure times the change in volume for a gas expanding or contracting at constant external pressure. When work is negative, we say that the system does work. When work is positive, we say that the surroundings does work on the system. Combining the definitions and symbols for heat and work with the first law of thermodynamics, we can write a new equation that delta E, or the change in internal energy, is equal to Q plus W. This is an important equation that we'll be using later in the chapter. I also want to take a moment to define temperature. For chemists, temperature is a property of a system that reflects the random motions of particles in that system. Concepts like energy and temperature are sometimes difficult to understand because they're fairly abstract and are often measured only as differences. For example, think about how we measure temperature. We measure temperature by the volume change of a liquid like mercury in a glass tube. But reality, what does volume really have to do with temperature? We also need to review the definitions of system and surroundings. The system is the part of the universe under consideration, and the surroundings would be everything else. Systems can be open, closed, or isolated. Open systems are systems that can exchange mass and energy with the surroundings. These systems are more complicated to study and are often not considered in chemical reactions. Closed systems can only exchange energy with the surroundings. Isolated systems are systems that cannot exchange either energy or matter with its surroundings. We also need to remember the definition of pathways and state functions. A pathway is a process for getting from one state to another. A state function is a property of a system that is independent of the pathway, independent of how it got there. In thermodynamics, state functions are given symbols with capital letters, and non-state functions are given symbols with lowercase letters. For example, we'll see how work, lowercase w, and heat, lowercase q, are not state functions. The heat and work associated with a transformation depend upon how that process is carried out. One of the state functions that we learned in first semester general chemistry is called enthalpy. Enthalpy is the heat transferred by a system at constant pressure. Enthalpy is given the symbol capital H. Notice that this is a capital letter because it is a state function. Enthalpy can be calculated from the equation H is equal to E plus PV, where E is internal energy and P is pressure and V is volume. However, since we can't really measure the absolute enthalpy of something, we generally talk about delta H, or the change in enthalpy, as being delta H is equal to delta E plus the quantity delta PV. Delta is the symbol that we use to mean change in, and is always taken to be the final minus the initial value. So the change in temperature, for example, is given as delta T and would be the final temperature minus the initial temperature. Back to our enthalpy equation. We often work with systems at constant pressure. We can rewrite this equation as delta H is equal to delta E plus P delta V when the pressure is constant. But since delta E is equal to Q plus W and P delta V is negative work at constant pressure, we have the expression that delta H is Q plus W minus W, which simplifies to delta H is equal to Q. The P subscript stands to remind us that this equation is valid at constant pressure. This means that we can measure the enthalpy change for a reaction as the amount of heat gained or lost at constant pressure. We need a way to organize and standardize the data we gather about heat exchanges for chemical reactions. So we define something called the standard enthalpies of formation. Standard enthalpies of formation are the enthalpy changes for the reactions that form 1 mole of a compound from its constituent elements in their standard states. Standard enthalpies of formation are symbolized by delta H F naught. The F stands for formation, and the superscript 0 indicates that all species are in their standard states. For example, the enthalpy of formation of ammonia is the enthalpy change for the reaction that forms 1 mole of ammonia gas from a half a mole of nitrogen gas and 3/2 of a mole of hydrogen gas. This reaction has an enthalpy change of negative 45.9 kilojoules per mole. Notice that the reaction is given in terms of 1 mole of the product, which sometimes will mean that we need to use fractions as coefficients for our reactants. Standard states refer to the conditions of the reactants and products. If the chemical species is a gas, the standard state will be when the pressure is equal to 1 bar. If the chemical species is an element, the standard state is the most stable form of that element at that pressure. If the species is dissolved in water, the standard state is for the concentration to be 1 molar. Note that temperature is not part of the standard state conditions. However, the enthalpy of formation values given in tables are generally for a specific temperature, usually 25 degrees Celsius. We use tables of standard enthalpies of formation and a principle called Hess's law to calculate the enthalpy changes for other reactions. The standard enthalpy change for a chemical reaction is given by the sum of the standard enthalpies of formation of all the products multiplied by the coefficients in the balanced chemical equation minus the sum of the standard enthalpies of formation of the reactants, also multiplied by their coefficients. For example, for the reaction of 2A plus B goes to 3C, the standard enthalpy for that reaction would be 3 times the standard enthalpy of formation of C minus 2 times the standard enthalpy of formation of A minus the standard enthalpy of formation of B. In Chapter 16, we will need to be able to calculate the standard enthalpies of reaction using the standard enthalpies of formation that can be found in Appendix G of your textbook. Notice that the units for standard enthalpies of formation are kilojoules per mole. Hopefully this review of the important concepts in Chapter 5 has refreshed your memory, and you're now ready to begin Chapter 16.